Okay, so from Chem 1, remember we had the reactions that we did them in nice, neat little categories. It's not quite the same in AP. There's different kinds that fit in different categories. But first of all, remember decomposition reactions. That's where you have one reactant and it breaks down into simpler substances. And we had a whole list of things that we did. For instance, metal carbonates break down into metal oxide and CO2, that sort of thing. And that's all listed in your notes. But for this one, molten sodium chloride, if we electrolyzed it, put an electric current through it, it would break down into its components, which are sodium and chlorine. So like an ionic compound, of course, it's going to break down into a metal and a nonmetal. And then some of your other ones are going to break down into different things, which we give you like a little basis of that. Compound may break down to produce an element or two elements, but it also may break down to produce a simpler compound and an element. In this case, this is hydrogen peroxide. And it decomposes catalytically. It also decomposes with time. That's why it's kept in a brown bottle. And if you have really old hydrogen peroxide, it's not, and you've ever poured it out, it doesn't fizz anymore. It's because basically it's just turned into water in there. Okay. It can break down to produce two compounds. Like we said, metal carbonate. This would break down to be magnesium oxide and CO2. Metal chlorate. Remember, like MgClO3, that breaks down to a metal chloride and oxygen. Whoops. Yeah. So there's that. Oh, it's not giving me the examples. So we'll do that. So MgClO3 would break down to be MgCl2 plus oxygen. And then we have to go back and balance that. Okay? So anytime you have the 3 and the 2 together, make a multiple of 6. So we're going to put 3 here, 2 there, and then that took care of our chlorine for us as well. If you have metallic sulfites, they break down into metallic oxides and sulfur dioxide. So let's say we have MgSO3. That's going to break down into MgO plus SO2. And that would already be balanced as is. So the way you recognize decomposition is you're always just going to have one reactant. And we just did this one, H. We did that one already. Sulfurous acid. Who knows the formula for sulfurous acid? I knew what you meant. You were just telling me which of the ones to use. I gotcha. So that's going to break down into water and sulfur dioxide. Okay? And it's already balanced. Carbonic acid. This is a big one. Okay? Never ever on an AP exam write carbonic acid as a product because it decomposes immediately upon forming. So it's going to be H2CO3, and that's going to make H2O and water. H2O and water. H2O and CO2. Sorry. But never write it as a product. That's like a biggie that always decomposes as soon as you form it. And so if you are doing a double replacement and you think it's forming carbonic acid, that needs to be something you ingrain in your head. Write it as H2O and CO2 because it immediately decomposes. So does sulfurous acid, the one we just saw, and ammonia hydroxide. NH4OH immediately decomposes into NH3 and H2O. So I just did that one. My thing is getting stuck. Did I skip one because it's being stuck on mine? Yeah. Hydrated salts. Whenever you have a hydrated salt, when you decompose it, it's going to just break apart the water. Okay. You can do this with copper sulfate. If we went into the lab, it's blue crystals, and we heated it gently, it would turn gray, and that's because the water is driven off, and then you have it without. But most of the time, if you just let copper sulfate crystallize, it takes in some water. Oh, you can go ahead. and leave that in the door. I had just taken it out at lunchtime. They're not there.
No, they're not there.
So someone did steal your AP Chem notes.
I guess so. There are 3 folders there, so.
Do you need a new? Do you need another copy?
It's fine.
Oh, I have one right here.
Okay, thanks. Thank you.
It's all good. Does anybody ever just call you Ben, or do they always call you Ben Quo?
Pretty much Ben Quo Ben.
Yeah. I mean, I'm just curious. I mean, I've had students over the years too that I never called them. That just like it, just your name just goes together.
It does.
Yeah. Ben Quo. I like it. I heard about you before you ever came to this class. It was good.
Okay.
It was good.
Like valedictorian good?
They did. They didn't actually just tell me that. They just said, "Oh, he's so nice. I really like him. He's a nice guy." Yeah. Oh, by the way, thank you very much. Miss Zimmerman said that y'all were fabulous yesterday. She said all my classes were just amazing. I was like, that's because I'm the luckiest teacher here because I have amazing kids. Addition reactions, if you remember from last year, sometimes we call them synthesis, sometimes we call them combination, sometimes composition. I don't know why they just can't pick a name. I personally like to call them composition because they're the opposite of decomposition. That makes sense to me. Because composition, we're putting 2 things together into one more complicated thing, and then decomposition, we're taking a complicated thing and breaking it down into 2 things. So it's when 2 or more elements or compounds combine to form a single product. Okay, so it's like the opposite. So that's why I usually call them composition. Okay. So those same things that we saw as decomposition, like a metal chlorate breaks down into a metal chloride and oxygen. Well, guess what? If I add a metal chloride plus oxygen, I make a metal chlorate. So it's like opposite. So last year I always said that you don't have to memorize it twice. It's just opposite. Group 1 and 2 metals will like to react with nonmetals to make a salt. And remember, salt's basically an ionic compound. You're made of more than salt. You have very little salt.
You're mostly water.
I think you're mostly sweet.
What?
You're always sweet to me. You're always sweet to me. Okay? A piece of lithium metal is dropped into a container of nitrogen gas. So come on, this thing is making me mad. So it would look like that. Lithium plus nitrogen makes lithium nitride, and then we balance that. Okay? 2 nonmetals may combine to form a molecular compound. In this case, we're forming carbon dioxide. Just some examples. When an element combines with a compound, you can usually sum up the elements on the product side. Okay? And then, of course, those are going to be molecular compounds there because they're both 2 nonmetals. Okay? Usually you can do that. You know, in chemistry, there's always an exception, right? 2 compounds can form a single product. If you're looking at something like this, ask yourself, is there a polyatomic with those 2 elements available? And hopefully you know your polyatomic, so you know that SO3 is a possibility, so you can add those 2 together and kind of make one of the polyatomics. If there's not a polyatomic that you're aware of, then you might have to question what kind of, is it, something different. So that's just kind of playing around with that. A metallic oxide plus carbon dioxide yields a metallic carbonate, which is the opposite of what we said in decomposition. A metallic carbonate breaks down into, So those are exactly opposite. So we really only have to memorize one of those and flip them. Okay? And flip them. Okay? Same thing with sulfur dioxide and a metallic oxide. We make sulfur, we make a metallic sulfite. So same thing we just did, and that's why I like those 2 together, because they're just opposite. Okay? A metallic oxide plus water will give you a metallic hydroxide. Okay, so I want to do an example of those. So if I like magnesium to do that because it's easy. So if I take magnesium oxide plus water, it's going to make a magnesium hydroxide. Okay. Sometimes we call those pretend bases because this right here is not necessarily a base, but if I add it to water, it's going to be basic. Okay. A non-metallic oxide plus water yields an acid. Okay. So let's say I have P2O5 and I add it to water. Okay. So it's going to make an acid. There's only two acids it can make. It can either make phosphoric acid or it's going to make phosphorus because we have PO3 and PO4. So when you're balancing these, I say work at it a little bit backwards. Okay. Regardless of whether I have PO3 or PO4, how many hydrogen am I going to have? 3. So I say write H3PO. We're going to leave it blank for a second. Okay. You can put a little X there if you want. So I'm going to balance my phosphorus by putting a 2 right here. Okay? And that means I have how many hydrogen? 6. So I need to put a 3 right there. So now how many total oxygen do I have over here? 8. So that means that that X has to be what? 4. So that means I have phosphoric acid. So those are just a little bit tricky because you're not sure is it going to make the PO3 or the PO4. So work that kind of that way. Did that make sense? Just kind of a little bit backwards, okay? Especially with your nitrogen oxides and your sulfur oxides, because you don't know if you're going to get the SO3 or the SO4, that kind of thing, okay? Double replacement, okay? Remember that's 2 compounds switch partners, basically, okay? There are no changes in oxidation numbers, okay? So we're still staying in the same oxidation state. All double replacement reactions must have something driving that force. They're going to be solutions because the ions have to be able to come in contact with each other. In AP Chem, unlike now, when we're practicing, you might see a no reaction, but on the test, you assume on the AP exam itself, you assume all reactions happen. They're not going to waste their time on giving you a no reaction. Okay, you just assume they all happen. Okay. Now, sometimes you got to pick out what was that precipitate. You have to pick that out, but you assume on an AP exam that they all happen. Okay, they don't. I've never ever seen a no reaction one. Okay, so the formation of the precipitant, of course, that's what y'all did in the gravimetric analysis lab. Two ions bind together. So you got to know your solubility rules to be able to write the net ionics. And this is where net ionics become very important. So these are just the basic solubility rules. Most nitrates are soluble. Actually, they're pretty much all. Okay. Most alkali group 1 metals and NH4 ammonium are soluble. I don't know why they're not saying all because I've seen most all the time they're all. So chlorine, bromine, iodine, remember they're soluble unless they're with one of those 3 heavy metals. Okay. Which is silver, mercury, and lead. Most sulfates are soluble except those barium, lead, silver, and calcium. And then most hydroxides, unless they're with a group 1 metal, are only slightly soluble. Okay? And remember, these rules are in order. So if you have an alkali, if you have a group 1 metal, assume it's going to, whatever it's with is going to be soluble so that it won't form a precipitant. And then most of these are only slightly soluble. Okay, unless it's with a group 1 or ammonium. Okay, this is a song that somebody wrote. I don't know if it actually plays. No, it doesn't. If you want to memorize that, you can. Okay, I wrote one a couple years ago to the tune of Rolling Stones' "I Can't Get No Satisfaction," but I can't find the words. But it's "I Can't Get No Precipitation." That's to the tune of that. One of my students and I sat down and wrote that together. It was kind of fun to see if I can find it. Maybe we could all sing it.
Yeah.
Yeah, I can't get no. So here we have an example of silver nitrate and lithium bromide. They're mixed. Did they give you that, or are we writing this in? Okay, so you're going to make silver. Oh, excuse me. I don't know if that was a hiccup, a burp, a cough. I don't know what that was. Just got to make up a new word for that one. So your precipitant is going to be your silver bromide because then it's an exception to one of the bromide. So if we were going to write that as, we'll do a net ionics in a little bit. Formation of a gas. These are those ones I was telling you that immediately break down. Okay? Immediately. Never write them as a product. If you think that's what they're making as a product, write them already broken down because it immediately decompose upon forming. So put you a star by that, circle it, because they do sometimes like to trick you with that one. So here we have excess hydrochloric acid solution is added to a solution of potassium sulfite. Okay. So what is that going to make? So that one is forming a gas. No, it's not. That's where you would write it like this. Sulfuric acid decomposes into water and sulfur dioxide. So it is forming a gas. I didn't see it. There it is. All right. So always write that down. Solution of sodium hydroxide is added to a solution of ammonium chloride. Remember that ammonium hydroxide does not exist. So we would write that down as, instead of writing NH4OH, we would write NH3 plus H2O. So those are all important exceptions to not write it as a product. Even though I can go back there and, I can buy crystallized ammonium hydroxide, and I can make a solution of ammonium hydroxide, but essentially it's ammonia in water now. Still basic. Is it a weak base or a strong base? Huh? It's a weak base. Good job. Formation of molecular substance, such as water or acetic acid. It's when the ions are removed from the solution and the reaction works. Okay? So here we have dilute solutions of lithium hydroxide and hydrobromic acid. And we would get lithium bromide and water. Okay? So what's the actual product being formed there if we were going to do a net ionic? H2O. If it's aqueous, it actually wouldn't be bound together. It would be swimming around in solution. But if you're making liquid water, then it is a product. And so we would write that as a net ionic. And we'll show you that when we get to net ionics. It's Friday, so I don't think I'm going to make y'all do net ionics today. Do that next week. Here we have gaseous hydrofluoric acid reacting with solid silicon dioxide. Okay, so the reaction occurs when the glass is etched. That's how we etch glass. And hydrofluoric acid, strong or weak acid? Weak. What are our 7? Everybody say, what are our 7 strong acids? What are you saying?
That's what Lawrence taught us.
What?
Pickle, hipper, high, clo, so.
I've never heard that before. HCl, the halogenic acids with the exception of HF, and then H2SO4, HNO3, and then HClO4 and HClO3. Yeah, I forgot. Yeah. Okay. But now this is a sidebar. You realize that just because it's not a strong acid in chemistry terms, it is still an acid that can hurt you, right? It's not. It's a relative. I mean, you got to think about what they mean by strong acid because hydrofluoric acid actually likes to bind with calcium. And where do you have calcium? In your bones, okay? So, yeah, you don't want to get that on you just because it says it's a weak acid. When they're talking strong and weak acids, remember, they're talking in terms of dissociation. They're not necessarily talking about in terms that will hurt you, okay? So don't think, oh, it's a weak acid. I can take a bath in it. Don't do that.
So will it, pull your skin away to get to your bone? What does it do to you?
Yeah, it's pretty much, anybody watch Breaking Bad?
Yes.
Isn't that how they dissolve bodies?
Yep.
I don't watch Breaking Bad from the sheer principle of the matter that I don't want these. Why are they making chemistry teachers bad? My daughter has watched it, my oldest daughter, and she knows me very well. She goes, Mom, you wouldn't like it. It's like, okay, then I'm not going to watch it. I will stick to... Does anybody watch This Is Us?
Yes, I watched that too.
Coming back, oh my gosh, I cry every September 26th. I hope my cable's working by then.
Miss Ghost is obsessed with that.
Who?
Eyewitness.
Like,
Great show.
what is it?
So it's about these two kids who witness a triple homicide.
I don't need any more depressing things in my life right now.
And then one of them's a foster kid, and they end up falling in love while they're being hunted by the killer because they're eyewitnesses, mind you.
Yeah.
Yeah.
Wow.
And one of them's a motorbike kid, and the other one's a.
And this is on Netflix?
No.
What's it
It's
on?
not a kids.
It's on.
Because all I can do right now is watch things on like Netflix, Amazon, because we don't have
Watch
our
Rick and
cable.
Morty.
Our cable's not working.
Wait, like, is there still the cable signal, or just like your receiver's not working?
Well, Xfinity is out, and we had to move all the stuff upstairs, so we have to have them come and run it to work upstairs for the next couple of months. So and then my friends were so kind to let us borrow their hotspot, and so yeah. Okay, single replacement. Remember, that's where you have an element and a compound reacting, and the element replaces either the metal or the non-metal. Depending on if your element is a metal, it's going to replace a metal. If your element's a non-metal, it's going to replace a non-metal, with the exception of, who remembers?
Hydrogen.
Hydrogen. Because in metals, well, they will react with acids, and so they'll replace the acids, the hydrogen and the acid. Again, when we're practicing these things, you might have some no reaction, but on an AP exam, if you see a single replacement, I don't even know if they give you the activity series, because they just tell you, assume that the reaction happens. But you have to know that a metal replaces a metal, and a non-metal replaces a non-metal, unless it's in acid, and in some water, okay? And in some water, okay? But that's where we would check our activity series. Normally, chlorine gas is bubbled through into a solution of potassium iodide. For the halogens, you literally can say fluorine will replace chlorine, chlorine will replace bromine, iodine can be replaced by bromine, iodine can't replace anything. You can go in order on those, okay? Because they get more active as you more active at the top, less active at the bottom. So in this one, the chlorine gas would make potassium chloride, and you'd get iodine as a element by itself. Kicks it to the curb. Iodine in its natural state is a solid, so you would need to know that that's a solid. Here you can tell on my periodic table which ones are the solids, which ones are the liquids, which is on the gas. The reds are gases, the blacks are solids, and the blues, which there's only two, are liquids. Okay, but you would need to know iodine are crystals in their natural state. Okay, everything else, these two would be aqueous, and then the chlorine, of course, is a gas because it says chlorine gas. Don't forget those. So there's your non-metals activity series. They're in order as they are in the group. Active metals replace less active metals. Okay, so lithium's at the top, platinum, gold, silver down at the bottom. Things that you would make jewelry out of, you want them to be not very active. We don't want our gold jewelry reacting with acid because we happen to be cleaning and we have vinegar or something. So hydrogen's kind of right there. Platinum is even less reactive than gold. Platinum is also more expensive than gold. Okay, that is not by any means all the metals. There's other metals that would fit in there at other places, but they're the ones you're going to see the most commonly. Lithium's the top dog. Okay. Magnesium turnings are added to a solution of iron 3 chloride. So we would look at that and say, will magnesium replace iron? Remember, if it's at the top of the list, it replaces anything that comes below it. If it's at the bottom of the list, it can't replace anything that comes above it. So look on there, will magnesium replace iron? Yes, it will. And so we would get this reaction. Magnesium plus iron 3 chloride gives me some iron and magnesium chloride. Again, paying attention to our states of matter. If I replace iron, we would see it in a solid. Now, if I was to do this in in solution, what would I start seeing? No, I'm not forming a gas. But I would drop the magnesium in there, and then eventually at some point I would get iron falling down at the bottom, and I could filter that out. Okay, we did that lab at pre-AP where we dropped aluminum in there, and we asked y'all what happened, and a lot of people said it was rusting. but it wasn't actually rusting. It was the copper coming out of the solution. Yeah. Do y'all remember that, lab? Yeah, because everybody says, it's rusting. Like, no, aluminum doesn't rust. Yeah, but it's the same color, but it's the copper. Sodium added to water, it absolutely will happen. It happens in an explosive manner. So sodium replaces the hydrogen, and that produces hydrogen gas. And remember, don't just write H by itself, because it is hydrogen gas, and that is one of our diatomic elements, our Brinkelhoffs. Did Miss Lawrence use Brinkelhoff?
Yes.
Okay. So it's one of our Brinkelhoffs, so you have to write it as H2. Combustion reactions, what do they always make?
Water.
Water and CO2. Okay. Sometimes we'll have some with other things like sulfur, that kind of thing, but most of our combustions are going to be CO2 and water. Hydrocarbons are alcohols combined with oxygen to form CO2 and water. Non-metallic hydrides combine with oxygen to form oxides and water. Not as common that we see those, but they're non-metallic. Sulfides will form oxides and CO2. Basically, you substitute the carbon for a nitrogen or a sulfur in one of those. Does that make sense? Carbon disulfide vapor is burned in excess oxygen. So it would look like that. Okay? But mostly our combustions are going to be hydrocarbons. That's what we mostly do. Ethanol is burned completely in air. So it looks like that. Do I need to practice bouncing some hydrocarbon ones, or are y'all good with that? Remember to save oxygen for last when you're balancing. Diethyl ether is burned in air. That's a nice, fun, complicated one because they put that oxygen in the middle and the CO2s. The other way that you could write this, I mean, if it helped you to balance it better, you could go ahead and say C. I thought I hit the pen. If you look at that and go, that confuses me, you can rewrite that as C4H10O, and that might make it a little bit easier. That's the organic way of writing it because that's the order it comes in the formula. But if you see something like that and you're like, oh my gosh, that's going to be so hard, just put them together. Okay, just put them together. And then we're going to stop there because then that takes us to net ionics.
Do you have to put it back in the natural form after you?
If you were doing it on a test, no.
Okay.
No, because I mean it's gonna be balanced the same. But that written that way is kind of like and then it's much easier to forget that there was 2 extra carbon in there. So I personally would put it the way I wrote it and then balance it because it's easier.
Okay.
Okay. All right, so we're gonna stop there.